All right, let's talk about math. And more specifically, how do we teach it so that it actually sticks and makes sense? We're going to toss out the old ideas of just drilling and memorizing facts. Instead, we're diving deep into what it means to teach for real, genuine understanding, using Lesson 3 from the Stadio Study Guide as our map.
So let's kick things off with the big question. The one that every teacher and parent has probably asked themselves at some point. How do we get math to feel less like a list of instructions to follow and more like something that kids intuitively get?
Well, it really boils down to this, a tale of two understandings. On one side, we have what's called instrumental understanding. That's knowing a rule, like with fractions, what you do to the top, you do to the bottom. You know how to do it. But on the other side, and this is the goal, is relational understanding. That's knowing why. It's seeing that the shaded part of the pizza is the same amount even if you cut it into more smaller slices. That's the deep connection we're after.
Okay, so here's our game plan for digging into this. We'll start by really unpacking that why before the how. Then we'll get into the absolute foundation of math, place value. After that, we'll talk about moving past just memorizing and how to get students to come up with their own clever ways to solve problems. Then we'll see how this pops up in the real world, and we'll finish up by looking at what true math fluency really looks like. So let's jump right in and really get a solid grip on the difference between these two ways of knowing math.
Relational understanding. This is our North Star. It's not just about knowing the steps to get an answer. It's about seeing the whole map. It's like building this incredible network in your brain where every new math idea connects to something you already know, creating this strong, flexible web of knowledge.
And then there's instrumental understanding. This is what happens when those connections are missing. It's kind of like following a recipe word for word, but having no clue what baking soda actually does. Sure, you might end up with a cake, but if you're missing an ingredient, you're totally stuck. You can't adapt, you can't solve a new problem because you don't get the principles behind it all.
Okay, so if relational understanding is the big goal, where on earth do we begin? Well, the whole journey starts with the absolute bedrock of our number system, place value.
Seriously, think about it like building a house. You would never ever start putting up the walls and the roof without a rock-solid foundation, right? In the world of math, place value is that foundation. It's this simple but brilliant idea that a digit, say a 5, can mean 5 or 50 or even 500, just depending on where it sits. It's all about grouping in tens.
Now, for a young kid, that's a pretty heavy concept, so we've got to make it real, something they can touch. We start with things they can physically group themselves, like a pile of beans or some cubes. Then we can introduce stuff that's already grouped, like base 10 blocks. And from there, we can move to more abstract tools like an abacus. We're guiding them from the physical to the purely mental.
And check this out. This is a fantastic example of how we do that. These are called flard cards. They are an amazing tool for showing kids how numbers are put together. A student can literally take the number 29 and physically pull it apart to see the 20 and the 9 that are hiding in there. It's not a magic trick. It's just making that abstract idea of place value totally visible and concrete.
So once that place value foundation is nice and strong, what's next? Well, now learners need the right tools for the job. And this means mastering basic facts, but probably not in the way you remember from school.
See, this is not about mind-numbing drills. True mastery is actually a journey, and it happens in 3 phases. Phase 1 is where it all starts, counting, using your fingers, objects, whatever works. Then kids move into Phase 2, which is all about reasoning, using facts they already know to figure out ones they don't. And only after that do they hit Phase 3, real mastery, where the answer just comes to them, fast and accurate, no counting needed.
So what does that reasoning phase actually look like? Well, it's full of these really clever mental shortcuts. For a problem like 8 plus 7, a student might think, okay, I'll take 2 from the 7 to make my 8 a 10, and I've got 5 left over, so 15. Or for 7 plus 8, they might think, hey, I know 7 plus 7 is 14, and 8 is just one more, so it has to be 15. The whole idea is to build up this mental toolkit of strategies, so counting on your fingers becomes a backup plan, not the main event.
And this is where the real magic starts to happen. When you give kids this solid foundation of place value and these reasoning strategies, they stop just following procedures. They actually start inventing their own brilliant ways to solve problems. So instead of just mechanically doing the old carry the one algorithm, they start to develop their own methods. We call these invented strategies. And they're not mistakes, they are the absolute best sign of a deep, flexible number sense. It proves a student isn't just a robot following code. They're a mathematical thinker who gets how numbers can be pulled apart and put back together in different ways. And why do we want to encourage this? Well, the benefits are huge. The source material is crystal clear on this. When students use methods they've invented themselves, they make way fewer mistakes because the process actually makes sense to them. It means less reteaching later on, it builds a much stronger number sense, and it lays the perfect groundwork for mental math and estimation skills they'll need for the rest of their lives.
Let me show you a really common example of one of these invented strategies. It's called the split strategy.
So let's say you give a student the problem 53 plus 37. Instead of stacking them up, a kid using the split strategy just thinks about the place value. First, they pull out the tens. 50 plus 30 is 80. Easy. Then they pull out the ones. 3 plus 7 is 10. Also easy. And finally, they just combine those two results. 80 plus 10 is 90. It's clean, it makes total sense, and it reinforces their understanding of tens and ones. No mysterious carrying needed.
And here's the real payoff. All these foundational skills, they aren't just for abstract problems on a worksheet. They are absolutely essential for making sense of things like money and fractions in the real world.
Just look at this slide. Understanding that 1/2 is the same as 2/4, which is the same as 4/8, that is pure relational understanding. It's not about memorizing a rule, it's about seeing that the total amount of shaded area doesn't change. This idea of breaking a whole into equal parts is a direct, practical application of everything we've been talking about. So, let's zoom out for a second and pull all of these pieces together to look at the big picture, what it really means to foster true fluency in math. This quote from the study guide really nails it. The goal is to get away from that quiet classroom where everyone is just silently filling out a worksheet. It's about creating a dynamic space where kids are encouraged to do math, to talk about how they're thinking, to show their strategies with models, and to write down their own unique thought processes. It's active, it's messy, and it's how deep learning happens. And that really brings us to our final and most important question. This is the key takeaway. It's about shifting our focus from just teaching kids the right way to do a problem to building a classroom culture that celebrates the journey. So how can we create an environment where students feel safe and empowered not just to find answers, but to invent their own unique and powerful ways of getting there? Because when we do that, we know we've stopped just teaching rules and started building real, lasting understanding.